Hi there, welcome back. So today I'm going to show you how to calculate 100-year return period of flood flow and water level as well. This is called flood frequency analysis. So if you already have your time series data, if you collect the time series data for different stations, you have to find out that if your model boundary is certain length, and if you have to find out some stations flow rate where we have measured flow rate at the upstream of this model boundary, or if it is possible close to the upstream boundary of the model is the best one. So once you are collecting your flow rate for even 30 years or 40 years, then you can perform that flood frequency analysis. And how can you do that? I'm going to show you that one. And for the downstream water level boundary, we also have to collect the water level for a longer period, right? We may have water level for 15-minute interval, or we may have water level which is daily or monthly, whatever it is. We need to have the maximum value of the water level for 1 year. Then we need even minimum value as well. If we have the time series, we can calculate the maximum value, we can calculate the minimum value as well, and then we'll perform some statistical analysis that is called flood frequency analysis using accidents probability and non-accidents probability. So how can we do that? I'm gonna do everything in Excel, right? So I have the code. I can do that in MATLAB, or it is easy to do in Python as well, and you can even use the R programming language as well. So either way it will be useful for you, but I'm going to show you, because most of the student or people, they're familiar with Excel, they're comfortable in Excel as well. So I'm going to show you how can I do that, and it's not that hard, it's pretty simple. And then I'll even use that 100-year return period of this flood values, flow rate and water level, and 50-year. And if you want to calculate, because once we have the equation, then you can calculate for any year, 500 year, 1000 year, whatever it is. So we have to develop that equation. Okay, let me just quickly share my screen and show you what I have and how can I proceed with that one. So from the study area I have, what I did, I collected that water level. So these are the values you can see. These are basically, here can you see that? Yeah, these are water level values from 1965 to all the way to 2006, right? But it is not completed. But whatever it is, what you have to do, you have to be able to calculate that maximum value for each of these years, right? So for each year we have to be able to calculate. So what I did, I just splitted the year, and I splitted the year here manually, because I can calculate it using MATLAB code. I have the code. That is not that hard, it is pretty simple. If you can write the code, it will give you the maximum value for year, and if you specify, it will give you the minimum value as well. So for each year I just calculated the maximum value and minimum value, okay? And for other year, so I did it. And next, when I calculated that, somehow, right, you have to have that maximum and minimum value. You need maximum value for flood frequency analysis for the case that I'm gonna do in this HEC-RAS model. So after that, what I'm gonna do, I just made it as a descending order. For water level, okay, let me show you the water level. I have this thing for discharge as well. So here it is. I'm going to calculate 100-year of flood water level. So what I did, I have the values for 41 years, right? The data I have, but I don't have the value for 100 years. So how can I calculate the water level for 100 years of a flood? So I have to even, I have to do some calculation, and then we can find that out. So here's the equation. I'll use that one, not a problem. These are pretty simple equation. So what I did here, in order to do that, I have to even make this irrespective of the year. We have to just arrange these water level values in descending order. That means the maximum values will be here. Just forget about the year number, right? We can't even remember for which year the value was the maximum. We don't need that. We need only the values in ascending order, right? In a descending, for this case it is descending order. I'm just arranging here, and I'm just giving the rank. The first one, the highest value will be rank 1, and then it will be just decreasing up to the minimum value. So once I have the value for water level, I have the same case for flow rate as well. Let me show you that one. So here I have also a value these are the flow rate. Okay, I have the values for flow rate, and these are the values. I already tried this one. See, you can see the values, and you can see the maximum and minimum value. Yeah, apparently you may think, okay, this is the water level. No, these are the flow rate, right? So the maximum value is 696. These are the values in meter cube per second. So these are yearly maximum values. So I'm just extracting these values for upstream stations from upstream stations, and then I'm just tabulating these values as it is. So I have 2 stations for flow rate, and I also have 2 stations for water level as well. So I'm just gonna show you the calculation for only 1 stations, then we'll use that values in our model and we'll run it again, and I'll show you what will be the difference between the previous simulation and the recent one. So here it is. The maximum value for 30-year period is 10,800. So that is the rank 1, and just arranging right in a descending order. And I have another station, right? The station ID is 212, and then I also have the same value here. You can see I have the same value. The maximum, I have 40 year for that station. That is another station. So as many station as you have, it's I think useful. It's necessary for this flood frequency analysis. Then your prediction of water level or flow rate will be more accurate to design that breeze clearance. That's very important part of this modeling. Okay, now what I'm gonna do, I'm gonna follow this equation because I already have. So the first thing you have to do, you have to calculate the maximum water level or flow rate and arrange it in a descending order and give the rank as 1, 2. The minimum value will be the maximum rank. Okay, so then I'm going to show the calculation for this one 30, or the value. Okay, this one will be good. I guess we have values for 40 years. Okay, so here it is. If I let me just show you that what I'm giving here, the values in a maximum and as a descending order. And here is the calculation of accidents probability. So I'm going to calculate the accidents probability. So what is accidents probability? Accidents probability is nothing but it's kind of probability, a chance, right? The value should be within 1. The maximum value of probability is 1. We know that, right? So how can we define the accidents probability? It is nothing but a probability that a value will be exceeded in a predefined future time. So what will be the probability of a value? Like the maximum value of flow rate is 5207, right? So let me calculate the accidents probability of that. So the accident probability of the maximum value will be minimum, because if you want to exceed this value, the probability is less, right? If you have a lower value, then if we have any flood event, so there will be a high probability that, okay, this flood will be exceeded, right? Our 10-year flood or 20-year flood. But if it is 100-year flood, the value will be very high and the probability will be very less, because you won't see any 100-year flood every year, because that's why it is 100-year flood. You'll see that type of flood peak in once in a 100 year, right? So that's why the accidents probability will be very less. So what is the equation for calculating that one? I'm going to show you that. So since it is Excel, we can do the calculation. So it will be the rank divided by m plus n. What is the n? N is the total number of the value, right? We have 40, so we have to divide. So in Excel, I'm going to show you that. So who are people who wants to see some calculation in Excel, it is pretty simple. So in order to write any equation in Excel, you have to provide equal sign and then m, right? So that's the column. We have m. I'm going to give m and divide by n plus 1. What is n? N is 40 plus 1, right? If I hit enter, it is going to give us this value. And if I want to repeat all these calculations, just click on and double click on that. It will do the job for us, right? See, the accidents probability of the minimum flow rate is almost 1. That means it will be exceeded every year, right? We don't know. We can calculate the return period, then we'll see what will be the return period for this value 6.93. Okay, So then what you have to do, since it is exceedance probability, and then we'll calculate the non-exceedance probability. So the non-exceedance probability is nothing but 1 minus that value, okay? Because we know the total value of probability is 1. So 1 minus this value. So if I want to repeat everything, and then, so you see it is just opposing those values. The exceedance probability is this, and the non-exceedance probability is this. That means in a single year, this water level, it won't be exceeded by any other flow rate, right? This flow rate won't be exceeded with this value or any flood event. So that's why the value is close to 1. This is the probability for, right, making sure that, okay, this event won't happen. And then what will be the return period? If you know the non-exceedance probability, right, then it's pretty easy to calculate, right? The return period is 1 over P. So what is the value of P? It is the exceedance probability, and that's why I have to divide P exceedance, right, 1 divided by that exceedance probability. It is the opposite of that one. So we calculate this way to see. Okay, that's the year. See, we have 41 years. So if we have any flood event and the peak is this, it will take 41 years. You won't see this type of flow rate, right, every year. You can see once in 41 years. So that is the return period of this peak. But we want to design our breeze for 100 year of return period, but we don't have the value. So how can we extrapolate these values? So we have to make this relationship in between this time series values, right? Because we have values for 40 years. So we can utilize these values and we can even extrapolate, okay, we have this trend and we can find out the value for 41 years or for 100 year or 1000 year. So if your observed value is more than this, so your prediction will be more accurate. That's why you have to collect many stations and you can find which station has the maximum number of years, right? So the next thing we have to plot. We have to be able to plot this, right? That's why we calculated this one. I already plotted this everything and we'll figure it out. See, once you have this non-exceedance probability and then you have that return period, right, and then we can plot it. So I also have everything ready here. I'm just gonna show you quickly. That is the plot. After calculating, you just copy, right, copy this flow rate and the return period. So that's the relationship, because we want to provide the return period and we want to get the value, right? So in the x-axis you have to provide your return period, and in the y-axis you have to have your flow rate or water level, whatever it is. Okay, so here it is. I'm gonna show you pretty quickly. Okay, I'm gonna copy it so that you can understand that what I'm gonna do. So I can put it there. Okay, so that is the Q. Okay, Q flow rate. I'm gonna plot this way and insert, and if you go to there and you can plot it like any splines, anything, okay, or any curve, but this time we'll plot that way and we'll fit the curve. Okay, we'll fit the curve. We won't even use any line, anything. That is what I did here, right? That is what I did, and it will give us the relationship. So once we have that, because we have to calculate the relationship in between these two values, then we can get that equation, and once we will have the equation, we can calculate the value for 100 year, for 1000 year. Okay, this will be T, return period, and this will be in year. Okay, so I'm giving the name, and that will be Q, and in meter per second. Okay, Q means flow rate, meter cube per second. And I'm gonna just increase the number, and you can see that pretty quickly so that you can, yeah, it's visible. Okay, so that's that. So the next step is to, right, create a trend line. How can I do that? If you just right click or select one and right click, add trend line, so it will give you the default trend line as a straight line, but we won't use that because we have to fix, right? We have to even fit the curve, because see, the variation is not like a straight line. If you want to show the equation of the line, see what it will show you, that one, display the equation, and at the same time we have to display the correlation coefficient, right, in between these two. So it is 9722. So even we can use the same equation. It's pretty simple, and if you want to fit more accurately, you can even select any exponential, logarithmic, polynomial. Since it's looking like polynomial, so I'm gonna select is that polynomial, or you can select power as well. I'm gonna select polynomial, and you can check that when you can change the power or the order right here. You can change the order and it is gonna fit more accurately. See, now it's looking like pretty accurate, right? It's a 99 r square. You can check the r square. 1 is perfect, and for acceptable range it should be more than 0.6 to 1. So okay, I'm gonna accept this one. It's okay. See, so we have the values up to 45 years here, but if I am gonna extend it, so it will be following, right, this trend. And if I reduce, see, it is gonna show you the downward direction, so it won't help you. So you have to test. If I select this one, order 2, then I think it will be okay. If you even fit it perfectly, then your curve will be overfitting and it won't give you that. So that will be another problem. These are called statistical problems. We won't need any overfitting problem. If you perfectly fit your curve following every line, and it won't give you more accurate results. So we have to be able to find a equation for any line, right? Even it is not high, right? The correlation coefficient is not that high. It's okay, but you have to be able to find. And straight line is also good if this relationship is good, but for this case I'm not going to select any straight line. I'm going to select this equation 98 is okay. So once you have that, okay, once you have that equation, so how can you calculate return period? So I'm going to give you the value. So here is the return period, okay, the return period. Return period will be in year, okay, in year, and then here it will be your full discharge, okay. It will be in CMS, meter cube per second. That's it. And what you have to do, we'll use that equation. I'm gonna give you, because we don't have any value for even 50 years, right? So I'm gonna calculate the values for 25 years because we have the value within 25 years. So the value we'll get, it will be within our measured values. And then 50 year, and then 100 year, and then if you want, right, for any big breeze or for anything, you need to even calculate 500 year. We can check that, and we'll use these values in our model, and we'll see what is the effect of these values, right? And what will be the flow rate? Flow rate is nothing but, see, in this equation we can see the value of y, it is the flow rate, and the value of x, it is the value of return period. So if I give the return period, it will give me, right, it will give us the value of flow rate. So how can we do that? Let me just quickly zoom in so that you can see it pretty easily, right? So I have to write this equation here. How can I write that? So the variable is x. X means this return period. So I'm starting with equal sign since I'm writing as an equation. Then the first value will be minus, right, minus 1.1171 multiplied by, it will be square of x, means this value, right, this one. And how can I put this square? This is the square term. Then it will be plus, and 174.81 multiplied by x again, right, this value 81, this value, and then it will be minus 35.268. See, I'm just giving the x value as return period, and the coefficient are as it is, minus 1.1171, and square of return period plus 174.81 multiplied by the return period minus 30. This is the coefficient, right, 35.268. If I hit enter, it is giving me this value, and if I want to repeat everything, just double click, it is gonna give us these values. Can you see that the curve fitting, if I go up to 500 here, it is giving me these values, right, which is wrong. That's why what you need to do, if you just use straight line, if you instead of this one, if you just change your trend line, if you use straight line, let me show you what is going to give you. That's why you have to test. Okay, trend line. So the value, if it is linear, see, if I want to delete the previous one, I have this one. If I want to delete that trend line, and if I use my straight line, see, it is the most average straight line we have. And if I want to show the square root and the r square, still it is good. So for this case, if I use this equation, you'll decide. Okay, that is called from polynomial or polynomial equation, and that is from linear equation. Okay, it is also Q, flow rate. So I'm comparing, okay, so that you can understand what I'm gonna do here. So 134.3 multiplied by the return period plus 66.353. So this equation won't be negative anymore. And see, if I double click, it will give us the value, and that is the positive 1. So which one is accurate? What do you think? Definitely the linear relationship is accurate here, right? So if I compare the 25-year return period value, so from that polynomial we have 3600 and we have 3400, and for 50-year we have like 5900 and we have 6700, and for 100-year we have 62, and we have more than that, right? This is linear, so it is linearly increasing. So this is where we have problem, and here we can't get anything, and we have even values 67, right? So let me check you, let me show you the actual value, because we have the value of 25 years of return period, right? So let me find that value out. So what is the return period of 25? So we have 20 here, right? We have 20, and what is the value of this? It is 3300, right? 3300 for 20 years of return period, almost 20.5 years. This means 21 years. So if I add more, right, if I add 4 years, so it will be 25 years. That means the value will be more than 3359. So for this case, this is maybe accurate, this is maybe accurate, right? We don't know which one is more accurate, but for 100-year return period, to be on the safe side, which one you are going to select? Definitely, if you want to select, you should select, right? Yeah, for 100-year return period, we can go with our previous equation, the polynomial equation. But here you can see, since it is linear, it is linearly increasing, but the relationship is not linear. Here you can see most of these values are like non-linear here, but for higher flow, the equation is not polynomial. So that's why in my previous plot, see what I have used, I use that value polynomial, right? That one, exactly the same one I used previously. So if you use the same one, that is okay. So we can select this value. Okay, I'm selecting this value. Keep in mind that we have the flow rate, this one, and for water level, okay, we'll use this value 6274, or you can round it 63. Okay, 6300 meter cube per second. That is the 100-year of return period, and we can use that as a 6000, right? And we can use that as 3600. So we are gonna use these values as this one. So I'm gonna create another table where I'll use my, okay, I'm gonna create another table here so that you can understand what I'm gonna do. Return period, this is the flow rate, and I'm gonna round this to, okay, I'm gonna round this as integer, this one. Okay, we can exactly use that, or we can replace these values. 3600. This is the manipulation, because this is engineering. Okay, so we can use 5900, that's okay, and we can use that 6300, okay, because I'm just rounding within 6300. So these are the values. What will be the value of water level in meter? Okay, in meter from the datum, if you have any specific datum. So for water level, I have the values for 41 years, and I already just arranged these values as descending order. So what will be the accidents probability as before? The equation is written there, right? So that is the value of the rank, and you have to divide these values by your number 41, number of data plus 1, so it will give you the accidents probability. So the maximum value, it will have less minimum accidents probability. However, the value with the minimum value will have the maximum accidents probability. That's why we're going to calculate the non-accidents probability, because most of the time we use that non-accidents probability, so we don't want to exceed our value. So that's why we need to test if our non-accidents probability of our return period that we are going to use in our model is higher, right? So we are just caring about this one. That's how we can just calculate. So it will be 1 minus the accidents probability, and then it's going to give us 97.6, right? No, 97.6%. So if we have any value that is like close to this 6.72, so 97.6% out of 100, right? It won't exceed. That is the probability. It's close to 100%. That we can make sure that, okay, if you have any value, it won't even exceed for this return period. Let me just calculate the return period here. That will be 1 divided by the accidents probability. So that is the 42, right? So you are sure, 97.6% sure that this value won't be exceeded, right? Won't be exceeded within 42 years. So using these values, I'm gonna even calculate the same way I calculated the previous values here. Copy, and I'm just putting it there to plot, and then I'm selecting this 2, and then I'm just inserting and plotting this as point. See, the scenario is different here for water level as well, right? So definitely it is not gonna show you any linear relationship. What is that? It's definitely non-linear polynomial. I can see that. Even you can fit using your log. That's also, because this is gonna show you kind of log correlation, right? So we'll even use the log axis as well. The y-axis should be log, and you can use even log axis. It doesn't matter, whatever you like, you can do that, but you have to fix, right? And you have to test it. And I'm gonna show you this one. So that is the return period as it is, mean R, and that will be year, and this time it is water level, right? This is water level but in meter. And I'm gonna even select the trend line here, add trend line, and you can see I'm gonna select the trend line if it is there. And what will be the equation if I want to select this equation? And I'm gonna select, see, the relationship, linear relationship is 0.57, so it is not acceptable, right? So we have to change it, because I can see, right? I can see from my experience that this relationship is not linear anymore. It is even not exponential, right? It is opposite. So what is it? See, you can see the logarithmic option. If I select that logarithmic, it is gonna fit pretty accurately. Then you can see the 97, right? So that's what we have. So if I use the same technique here that I did for my other cases, right? So if I even want to show you the same type of calculation there, if I select this 2 and I'm copying it, and there I'm going to show you the same thing. Instead of discharge, this time it will be flow rate. Okay, this time it will be water, no, it will be water level instead of flow rate. So I'm gonna delete that, and then we don't need anything, any color, no field. And here I'm gonna use the same equation. So this time, for the first time, it will use, we don't need to even test with linear relationship or not. So it's gonna be 0.7203 multiplied by this log, right? So you have to use that log 10. Here it is definitely log, yeah, it is log, it will be log, log means it's log, and then it will be x means the return period, and then plus 4.505. okay, so that's that 5 point. This one, if I double click, we're gonna have this one. So let me check if we have 25 years, right? So what we're gonna get if it is 25 years. So this one, okay, the water level we have 6.61 right? Since it is 25 years, we got 5.51, but for 21 years, see the relationship is, for 21 years it is this, more than what we got for this one, right? So even we can fix that, even we can change the relationship here that we have. It doesn't matter if you want to change it. Instead of a logarithmic relationship, you can even change it to a different relationship. That's okay. Let me test you. If I can select the trend line, or we can select another trend line, that's also okay. And instead of this one, we can even select power this time. Okay, even we can select moving average. Whatever we can select, we can fix it, right? We selected logarithm, and we even didn't use anything, but we can select power. It will give you even different thing, right? So that's this is how we have to fix which one is giving you better result. So I tested many times, and I use even polynomial. It's not gonna give you the accurate result based on the value we have, right? So I tested everything, and I'm gonna show you what I have tested here, and maybe you are gonna see that. Maybe let me find it out. Okay, it should be, yeah, so you can see that what I have used. I use this one, and I'm gonna get 98.57. I got 98.57. okay, so this equation I have got, if I copy that and if I put it there, the value I have, so this is the difference, right? This is the difference. See the difference we have. If I increase that 6, you can see clearly, and I'm gonna compare with that equation. So that is 0.88. okay, that is 0.8852 multiplied by that return period plus 4.4862, and then no, wait, so that is the wrong thing I did. I have to provide equal sign and then 0.8852 multiplied by that logarithmic, okay, this one, and then it will be this value plus 4.4862. then we are gonna get this value 5.7. see, we have increased value, right? We increased the value a little bit, so we can even go with that one. So for 100 here we have 6.2, and if you have multiple stations, you can use that value for multiple stations, right? So for this case, for this real world scenario or the breeze I'm going to design, right, the vertical clearance and the horizontal span, and I'm going to calculate the scoring around the breeze pier. So the maximum flow rate I got is, I'll show you that one, and the maximum water level I got for 100 here is 7.85. okay, that is different case because I have used another station as well. I have many stations here. I have many stations. This is another one. I have another one. Okay, so I have many calculations. So I'll use this for this calculation. I'll use this value, right? Which one is greater? So 6.25. So I'm gonna copy this column and I'm gonna paste it there where I have this. Okay, so we have these values. So that will be 5.72. okay, I'm gonna increase it 5.75 because to be on the safe side. So I'm gonna use this as 6, and that is 6.25 means 6.5. okay, that will be our 100 year return period. So these are the values we just calculated here from plot frequency analysis, and then we are gonna use this profile in our model. Let me show you that one as well. Okay, how to create separate profile and plan, and I'll run the model right at the same time using all these values. Just keep in mind we have 25 years, 50 years, and 100 years. You can give these different options to your client because in order to design in a real world case, we have to give different types of options, right? And then based on the information and options, you can even decide which one you are gonna use. Okay, so that's that. I'm gonna open my model that we have here. You can see I have the model there, and I have the geometry as before. You can remember that one, right? So we have everything ready. So I'm gonna open the boundary condition, right? The steady flow data. So if I open it, you can see we have only one value for 100 here, right? So for 100 here, I use 5,500, but this time we have 6,300. So I'm gonna add more profile, right? That is what, because we're gonna give this at the very upstream, which is the number 20, right? So how many profile you need? We have 3, right? We have 3. If you just provide the number and apply data, it will give you that. So that, okay, let me just edit the value of the profile name. The first one, I'm gonna give this as 25 so that you can even follow. 25 year, that will be 50 year. So this is how we do things in real world cases, and that will be 100 years. So now you can remember, okay, which one is for which one. Okay, so for 25 year we have the flow rate 3600, and for 50 year we have 5900, and for 100 year the flow rate is 6300, right? So we have these values. So what do we need right now? We need to go to our water level, right? So I'm gonna save this. What I did, save flow data, it's saved. And if you wanna even add your water level boundary condition, you have to even do the same thing, right? Click there, and then what I did, I used that water level boundary condition here, known water level, right? Since it is water level boundary condition, we can give that, right? The boundary condition we've already provided. What was that? It was known water level, right? And I already provided that values here. So we know the 3600 is for what? Is for 25 year, right? And that is the value 5.75. From the left side, I'm reading that and putting it there. And for 50 years of return period, the value is 6.0. However, for 100 year, for this case, we have 6.5. Okay, so that's it. We have 3 different profiles, and I'm now saving it. I'm saving that flow data. So if I run the model with these 3 conditions, I'll have 3 different profiles. Okay, let me just go to run and open a steady flow condition. Let me check the profile we have here. Now I'm gonna create different profiles. Okay, we have 1 profile here. I have to create 3 different profiles or plan, right? So that is the condition we have. So here we have 100 year flood, and if I create a new plan, it will be okay. The new plan, you can even select that way, like 25 year, 50 and 100 here. Okay, 100 here, you can give any name you want, and then it is gonna ask you ID. I'm gonna give the ID as it is. Okay, the ID is already there, so we have to provide 02. The previous one was that one. See, so now if I run, so that will be my plan name. Okay, it is gonna save in a separate model name .02, and if I just run it, what will happen? See the subcritical flow, I'm selecting that one, and I can check if I have the flow distribution as okay. Let me just change it to 8 at the same time, because this is new plan, and 8 is okay. I'm going to select it as 8. Okay, then I'm going to select okay, and I'm going to save the plan since it is new plan. Then if you run it, let's see if there is nothing wrong. So it's checking, right, writing the geometry, and then because we have different plans, and it's going to run pretty quickly. See, it took 8 seconds, right? But previously it was taking only 2 seconds or 3. I can remember that one because it is running for multiple years, and it completed that one. So let me just quickly open that. How can you open that? We can even open geometry. We can open the cross section from here, right? So that is the cross sectional value. You can see nice and clean. That is the most upstream one. And can you see that other information? You can see only one line there, right? You can see the legend at the same time. If I just minimize these values, you can see the legend. Let me quickly increase it a little bit so that you can even understand what I'm going to show you. Okay, I'm just displaying these values this way, and I'm going to close it. I'm going to open the cross section from here. You can see it's pretty clean and nice. That is the most upstream section. You can see the velocity, right? On the outer bank we have the maximum velocity, and then if I go next, it's going to give us the flow rate. But the most important thing, did you mention, can you recognize that? So we only have which one? Water surface elevation, that is right 25 year. So if I go to options, and here, can you find anything here to change the profile? In the plot, you can even plot profile, right? We have this profile there, and that profile, you can see, I'm just comparing side by side. You can see there which one, water surface 25 years, and this is the water surface elevation, that is even energy level, energy grid line for 25 years, and it is showing the critical, right? It is also for 25 years, the red dot. But if you want to even show the other profile as well, you have to go to options and then profiles, and if you want to even change the plan, you can do that. So let me select the profile. See, we only have one profile. If you want to select all, and if you put it there, now it will show you the three different profiles together, right? Now we can compare which one is higher and which one is lower, right? Definitely the water level with, or flow rate with 100 here will be higher than that. So you can see which one is 100 here, the green, right? The upper one, and the blue line is for 50 years. And then the black one is for, right, 25 years, the blue, and without that star. So we have these profiles. So these are the options we have. So you can select which one for which one. If I select 100, if you won't understand by your naked eye, you can select there, and that is the 100 here. Definitely it should be the highest water level or profile level. And if you select 50 year, it is lower than that. And if you select 25 year, right, so that's that. These are the energy level. If you want to see the right energy grid line, you can see that. If you see water surface elevation, you can select water surface. So that is the water surface elevation here for 100 year. If you want to see the water surface elevation for 50 year, you can see that water surface elevation here. And for 25 year, you can see that 25 year is there. So that is the 25 years, and that is the 50 year, that is the 100 year. So if you want to design any breeze, that is for 25 years, and if you have any flood that is for 100 year, then definitely the breeze will be flooded, right? So it won't sustain. It may be collapsed, or it may be, there may be different issues. The breeze will be submerged. So that's why you have to design the breeze at least for 100 year. Then your breeze level, the bottom chord of the breeze will be here at least. So I'll show you how to even design that level, and after calculating all this thing, we have to provide some factor of safety. And based on this information, if your water level is here, because 100 year water level will be here, and if your breeze is here, then their own, right, it won't pass any vehicle, any water vehicle, any ship won't be passing, right? Because it is just it will touch the bottom of the breeze. So from that level, when the flood level will be 100 here, that means your water surface level will be here, and from this level you have to fix your breeze clearance, the bottom of the breeze, right? It will be there, or yeah, we will have that calculation based on the navigation route. So from 100 year return period of flood level, you have to fix the bottom chord of your breeze. So then if your water level is higher, even for 100 year flood, definitely the size of the ship, if it is allowed for class 1 navigation route, or whatever the number of the navigation route, definitely it will pass. So that is the engineering decision you have to make. and you have to give these options. If it is 25 year, it's there, and if it is 100 year, it will be there. So these are the decisions you have to make as an engineer, and you can even try that one. So next time what I'll show, I'll add the breeze, right? Our breeze section will be there in between section number 4 and section number 3. Here we'll provide our breeze. So I'll use that breeze and culvert, and I'll show you how to insert the breeze piers and how to insert other information as a breeze. So in the next tutorial I'll show that. Then I'll run the model again with breeze. By this time you know how to develop the geometry from survey data that we already have, and I uploaded this survey data in the previous video. You can click the link in the description, then you will be able to access that one. And now we know how to, you don't need to analyze this one. If you have data, sample data, you can even analyze this flood frequency analysis, or you can, for this calculation, you know the maximum and minimum value from this video, you can directly use that, but you know how to calculate this, right? Flood frequency analysis. That's that. In the next video I'll cover breeze scoring, and then there are different equations as well. So you have to calculate the scoring using empirical equation and using this model, and you have to compare which one is giving you the highest value. So to be on the safe side, you have to use the highest value as well, and after that we have to apply some factor of safety, right? So your calculation may be wrong, or because we are using only the empirical equation, but in reality the situation may be different than what we are expecting here, right? That's why we have to apply, usually as an engineer we apply this, the customs we apply, right, a factor of safety. Then definitely if the construction is okay as designed or as preferred by the other engineer, structural engineer, everything is okay and the construction is okay, if the quality is maintained properly, and then definitely the breeze will even sustain, right, if there is any flood, 100-year return period of flood. So that's that. So you can try by yourself. If you have any query or question, you can just shoot it in the comment box, or if you have any other issues, you can even find different materials. And for the best one is to go to help menu here, and then you can find the manual, right, how to enter geometry, how to enter this thing and that thing. So that's why I always prefer to read their manual, because they have some sample example, but they sometimes they also give you the data and values, and you can even practice that one. But maybe sometimes you'll have some issues with how to do this, do that. So you can even use this video series to repeat your task. So good luck for you, and then stay safe and see you in the next tutorial. Thank you very much for watching this video.